this works. Okay, welcome everyone. Good afternoon. It's my great pleasure to introduce Professor Felix Otto from Leipzig. So before we start, let me just say a few words about him. So Professor Felix Otto obtained his PhD thesis in Bonn under the supervision of Stefan Lukaus. After being a professor at Santa Barbara in California, he was professor at the University of Bonn, and he's now one of the directors of the Max Planck Institute of Mathematics. And he's leading, in particular, the research group on pattern formation, energy landscapes, and scaling laws. Among many awards, he received the Leibniz Prize from the German Research Foundation in 2006, and very recently, the prestigious Cantor Medal from the German Mathematical Society for his work of exceptional depth and highest impact on the fields of analysis and partial differential equations. His research focuses on models coming from material science and fluid mechanics. You may have heard of him for the Otto calculus, the JKO scheme, JK Otto scheme, or the Otto Villani theorem in optimal transport. In fact, today he's going to talk about the variational regularity theory for optimal transportation and its application to matching. Thank you very much for being here.
Thank you very much. I hope you can hear me. Is it working? It doesn't sound.
Maybe if you put it a little bit like, is it on? Is it on mute? Okay, is it on? Be hearing something. Sorry.
Go ahead.
Please. Is it okay?
Yeah. If it works, does it work? Yeah. So does it work now? Okay. Yeah. So I'm still speaking at the same. Perhaps I can take the other one. Now something changed. Yeah. Is it better now?
Okay.
Very good. Okay. Thank you very much. Thank you very much for the invitation. It's a real pleasure to be here. It's my first time in Padua, and of course I knew about the famous and big math department before, but I didn't know the very nice city. So what I'm going to talk about is joint work, which I started with Michael Goldman a while ago when he was postdoc in Leipzig, and I will also report on work with with him and Martin Huisman, and a joint PhD student of Martin, former PhD student of Martin and myself, Francesco Matessini, and it is connected to optimal transportation. And in fact, kind of a regularity theory for optimal transportation, which is inspired by the regularity theory for minimal surfaces. And but in order not to start in a technical way, I want to start with an application to something which doesn't have to do anything to do with partial differential equations or even with regularity theory, and that's the problem of optimal matching. And in a certain sense, I want to use this as a teaser. So the first part of my talk will be kind of perhaps even a bit more probabilistic or statistic than related to partial differential equations. Okay, so now I'm pushing this the wrong way. Okay, that's the right way. So I start with kind of almost kind of a combinatorial problem, which is the optimal matching of point clouds. So suppose you're given two finite point clouds in d-dimensional space, the blue and the red points, and now you want to match these points in an optimal way. And the optimal way means, in a certain sense, you want to minimize the distance between the matched points in one specific way. And one of the ways is to look at the match points. So the matching between this set of n objects and this set of n objects can be described by a permutation sigma. So sigma of n is the point, the red point. Y sigma of n is the position of the red point, which is matched to the blue point with index n. And you look at their Euclidean distance, and you raise it to the power p, and you take the sum. And so that you might consider as a cost functional of the matching, and you want to find a permutation which minimizes that cost function, right? So that would be a version of optimal matching. Let me point out that it does depend in a somewhat subtle way on the exponent p you're putting here, and a very simple example of this is what I drew here. So suppose your points sets just consist of 2 points, 2 blue and 2 red points, and they're almost all on one line, and 2 points are further removed than these two. Then for p equal to 1, the optimal choice would be this, because it's by the triangle inequality you can convince yourself that whatever is optimal should not lead to crossing of the segments which connect the matched points. So that would be the optimal choice for p equal to 1, but which means one of them is pretty short and one of them is pretty large. Now, if you kind of take a different power here, so in a certain sense you penalize large distances more by going to p equal to 2, that would be the optimal matching. So which matching you get depends on which problem you're considering. Another observation is, and that makes this, gives this problem a certain complexity, is that you cannot check which matching is optimal just by kind of looking at transpositions, just kind of reassigning, 2 points or a pair of 2 points. So there, the simplest example would be the following. So you have the blue points, which are arranged in an equilateral triangle, and the red points sit almost in the midpoints of the connecting edges, but slightly biased towards one of the 2 corners, so like here. And let's look at this matching here, which is clearly not the optimal one. The optimal one is this one here. But you could not find out that this is not optimal just by reassigning, by switching the partners of x1 and x2 as indicated here. So because that would, substantially increase the cost. So by just looking, by switching partners of two points, you wouldn't detect that your global minimum is over there. So in a certain sense, you may say that from a point of view of complexity theory, this is a difficult problem, and in principle, you would really have to check, the number of permutations and factorial permutations to find out the optimizer. So here is kind of a numerical exploration where, in a certain sense, the algorithm runs through in a smart way through all the possible permutations. Here, one way of kind of visualizing this is to put the points in 2 different planes. Of course, they're in the same space, but if you separate them, then you can clearly see which ones are being connected. And you can imagine that this turns into a pretty kind of high complexity problem if the number of points is large. Okay, so now let's add an additional layer to this problem by not looking at kind of given point configurations, but by looking at random point configurations. And kind of the most natural, or let's say the least biased way of introducing random point clouds, let's say all within kind of a box of a given side length L, as indicated here, is what's called shot noise. And here you see kind of one realization of shot noise being built up. So I think shot noise is a pretty suggestive name. But what it means mathematically is that you take, let's say, the blue points, which are numerated by 1 to capital N, to be each of them uniformly distributed, so according to the Lebesgue measure, if you want, and independently chosen from each other. And then you would get this kind of random point cloud, a random point cloud of blue points, and random point clouds of red points. And so for this to work, I'm always thinking of the volume to be an integer, so that so L to be the side length to be an integer, so that the volume is an integer, and I'm taking exactly the amount of points, so that there is 1 point per area or per volume, so that the typical distance between the points is of order 1. So let's look at this. Let's look at this random point process a little bit more closely, because that's related to something which is well known in statistics, which is the Poisson point process, which this slide is to explain. Namely, if I take this this construction on the previous slide of taking random uniformly distributed points, roughly speaking 1 per unit volume, and I let the sides of my system go to infinity, then I get something which stabilizes, kind of a point process which is well defined in the whole space, which is called Poisson point process. And you can see this, that this is something that makes sense by this numerical experiment. So here, let's assume, let's think of the system as being extremely large. And now we look at some arbitrarily chosen test subsystem, here this square box, and we look at kind of the number of points inside this box. That's kind of a random number. And we look at how this random number is distributed. And here now I'm already, a little bit too late. This is kind of a binning of this random number variable. And you see that this kind of approaches a stable distribution. And in fact, it approaches what's called the Poisson distribution, which is kind of one of the simplest random distribution on the natural numbers, which is given by this formula through the exponential function. So that tells you that in a certain sense, the statistics here in this subsystem becomes pretty independent of your system size. And that's the way how you introduce what's the Poisson point process. So it's a random arrangement of points, a random cluster of points, of infinitely many points, which is characterized by two properties. So if you have two disjoint subsets of your Euclidean space, you can look at the number of points in here and the number of points in there. Those are two random variables. And the first axiom is that these two random variables are statistically independent. And the second axiom is that if you look at one of them, this random variable is exactly distributed according to the Poisson point process with an expectation which is exactly given by the Lebesgue volume of the set. So by the volume V, V stands for volume. So that would be kind of a definition of the Poisson point process. So how you can give sense to this random point arrangement if you're looking at infinite space. But if you find that a bit, if you feel a bit uneasy about it, it's perfectly fine to think about this simpler definition where you have a large box and you throw kind of uniformly distributed independent random points into this box, and the number of points is equal to the volume. So that's the type of kind of point clouds I want to look at, or people have been looking at. So since the 80s of last century, and now again you can ask the question, what can you say about matching these random point clouds? And now that's a little bit subtle because those are infinitely many points, so you can no longer write down in a naive way, this variational problem, because whatever you do, the energy would be infinity. But what you can impose is that it's kind of optimal given its own boundary conditions, or to put it differently, whenever a matching is optimal, whenever it has the following property: if you look at a finite number of matched points, and you would reassign them by an arbitrary permutation of these points, then this would only lead to an increase of the cost which is associated to these points. So that's a definition which makes sense even if you have infinitely many of these points. And but clearly, in a certain sense, you wouldn't expect that the optimal matching is unique. And in fact, if you look at the one-dimensional problem, you see the non-uniqueness is kind of easy to understand. So here is kind of a graphical representation, a visual representation of the one-dimensional setting. So we have kind of the infinite line, and the blue points are kind of a realization of the Poisson point process, very much zoomed out. So the distance of the points is order 1, but we're looking at this from very far. And you have the blue points, and it's easy to see that a matching is optimal in the sense which I defined before, if and only if this matching is monotone. So if, again, these kind of connecting lines don't cross. So that implies that exactly tells you what kind of degree of freedom you have in kind of the trivial or not so interesting one-dimensional case. So you have to kind of fix one coupling somewhere in the center of your universe at the origin, and then everything is determined from the left hand to the right. And if you do that, you realize that something unexpected happens. Besides the fact that next to every blue point you find a red point, this matching becomes very biased. So if you move away from where you've chosen your original couple, you find out that kind of you start to match points which are extremely far away, and the typical distance of the matched points as you move towards either end diverges like the square root of the distance to the origin, to this somewhat artificially chosen origin. So in the 1D case, kind of this problem is, the 1D case shows that this problem is comes with a certain surprise. You would think that since in the neighborhood of every blue point you find a red point, that you would be able to match them optimally in a way where matched points are not far from each other. But this shows that this is not the case. So what's the reason for this? The reason for this is that the number densities of these points kind of still fluctuates on large scales. So what do I mean by this? I try to highlight this by this numerical experiment again. So we're looking at a pretty large system, I think 100 times 100, and we divide it up in 16 kind of artificial subsystems, 25 times 25. And let's look at one of the subsystems. And depending on which realization you take, the number of points in there fluctuates quite a bit. And you can see that more clearly by looking at the number density. So the number of points divided by the volume. That should be a quantity which has expectation exactly equal to 1, but it's never exactly equal to 1. So here you see these numbers as they fluctuate and from subsystem to subsystem. And in particular, if you would freeze a realization, they would be different for every of these 16 subsystems. So there are kind of mesoscopic fluctuations in the number densities. And if you've seen a little bit of probability theory, you know that essentially the size of these fluctuations are determined by what's called the central limit theorem or the central limit theorem scaling. So the size of the magnitude, the order of magnitude of these number density fluctuations scale like 1 over the square root of the volume. And now you see that this tells you that in a certain sense there is a chance that in higher dimensions the situation might get better, because if you look at these fluctuations in this subsystem, then they're of the order of the lateral length of the subsystem, which is L to the power minus dimension over 2. So that becomes smaller as the dimension becomes larger. So in higher dimensions, we might be better off when it comes to this phenomenon that the fluctuations go down. And there is indeed kind of a nice physicist type back of the envelope calculation which shows you that the two-dimensional case is the interesting or the critical case. So again, now I want to explain that here. So again, we're looking at two independent realizations of this Poisson point process, so this random infinite red and blue point cloud. And we know that if we look at kind of some artificial subsystem of lateral size L, that the number of blue and red points is not exactly equal to the volume, but slightly above or below. So let's look at the blue points, and let's assume that the number of points is above average. So, and as we've seen, the excess number should scale like the volume, like the square root of the volume. So we have, in a certain sense, a little bit too many blue particles in this subsystem, and they have to find a partner, a red partner. And they couldn't find it within the subsystem because there are too many blue and too few red. So they have to go a little bit outside of this subsystem, and hopefully just in an order 1 neighborhood, they find enough partners just outside of this subsystem. So that's the question, is that possible? So what you have to compare, you have to compare the number of the typical number of excess particles, excess blue particles in the subsystem with, the expected number of red particles in this neighborhood. So one goes like the square root of the volume, and the other one has surface scaling. And now, as they say in the US, you do the math. These two kind of numbers exactly are, these two exponents are exactly the same if the dimension is equal to 2. So if the dimension is larger than 2, there will be always enough particles in your neighborhood to be able to, find a partner. If in one dimension, as we've seen before, that never works. And the interesting case, the critical dimension in the language of statistical mechanics, if you want, is the two-dimensional case. So what can be expected in the two-dimensional case? So as you could imagine, I didn't invent this problem. In fact, this problem has quite a long history. So I think it started in the kind of Budapest School of Combinatorics in the 80s. But then it was taken up by probability theory. So Talagrand worked on this problem. And then, interestingly, more recently in Italy, it was kind of taken up by physicists, so by Parisi and his co-workers, and by analysts by the Pisa School. And so let me explain you in a nutshell what the very first result from the Budapest School states. So they were looking, in fact, at the original problem where you have a finite system, finite by large system, uniformly distributed points. The typical distance between the points is order 1, so you have the blue and the red points. And they were monitoring the minimal cost. So that's the minimum overall permutations of this, if you want, cost of matching with a power p, which is between 1 but strictly less than infinity. And then they were looking at the expectation of this number, because that's still a random number, because the points are random and therefore the permutation is random. And they were looking at kind of the cost per number, so dividing by n, and then taking the pth root to compensate for the pth power. So the quantity on the left-hand side should be, could be interpreted as the average distance by which one particle is being transported. And not surprisingly, so from what I've shown before, in one space dimension, they find that it diverges like the square root of the system size. And in dimension larger than 2, they find kind of what we would like to be, that it's bounded, order 1. And the interesting case is the two-dimensional case, where you find a logarithmic behavior that's also not untypical for any critical dimension, now be it in analysis with Sobolev embeddings or be it in statistics. Then in the critical dimension, you get logarithms. And here you get the square root of a logarithm. And so that was their result, which they proved by upper and lower matching. In fact, Talagrand looked at the case for p equal to infinity, where you get the logarithm to the power 3/4, which is kind of a very deep result. This proof is not so hard, but quite inspiring. So that in a certain sense, I think, was a motivation for all the subsequent development in this area. And now let me again, I'm doing a teaser for optimal transportation. So let me tell you what the thing we contributed to this by using regularity theory for optimal transportation. And for that, I'm returning to the infinite system. So not this kind of finite system which the Hungarians, the Budapest mathematicians were looking at, but the infinite system. And I want to point out one kind of important feature of the Poisson-Point process. So one important feature of the Poisson-Point process is that it looks the same everywhere. Wherever you place yourself, wherever you look, it has the same statistical features. That's something which is called stationarity in certain areas. It goes by different names. So the Poisson-Point process is stationary, which means that under this probability measure, any point cloud and its shifted version have the same probability. So again, the Poisson-Point process looks the same everywhere. Now, the optimal matching we got in the one-dimensional case clearly does not have this property, because if you look at it, you clearly see that it looks quite different at the origin, where you choose your original matching from very far to the left and very far to the right. So that clearly is not stationary. You still see where you made this arbitrary choice of first matching. So, so the question is, in the two-dimensional case, are we able to match the points in an optimal and stationary way or not? So in the three-dimensional case, that's known to be true. But in the two-dimensional case, that was our result, that it cannot be done. So so Martin Hüßmann, our collaborator in the later work with his PhD advisor Karl Theodor Sturm, proved that in dimensions strictly larger than 2, and for any exponent down to 1, there is existence of a stationary and optimal matching. And we proved that also in dimension 2, which is kind of, in 1 it's obvious, but in dimension 2, there is non-existence, so non-existence proof. Unfortunately, we cannot quite get down to 1, and at the end, if you ask me, I can explain why we cannot cover this interesting case of p equal to 1, which perhaps is one of the most natural. Okay, so that was meant as a teaser. So this is kind of a statement which apparently doesn't have anything to do with PDE, doesn't have anything to do with kind of continuum properties. It looks like a completely discrete statistical statement, but what's inside the proof is PDE theory. So it was meant as a teaser also for those people who are not in PDE, to get you a little bit interested in what I'm going to tell you now on the side of analysis. And please interrupt me if you have questions. I'm not in a hurry. Perhaps you are. Okay, so now, I mean, I want to translate this problem, which again came as a combinatorial problem, as a discrete combinatorial problem, step by step into something that has to do with analysis that's more continuous. And the first step is, and that's perhaps almost obvious, that this problem is related to the kind of still vibrant problem of optimal transportation. And then I want to tell you that optimal transportation, in fact, is related to a very famous partial differential equation, which goes by the name of Monge-Ampère equation. So that's what I want to that's what I want to explain. That's what I want to explain now. So so this slide is kind of supposed to give you explain what the variational problem of optimal transportation is. It's in a certain sense the continuum version of optimal matching. But instead of looking at kind of discrete measures, so empirical measures, if you want, bunch of Dirac measures, you allow yourself full freedom, and you're given kind of two measures in RD which have the same mass. And in a certain sense, you want to transport the mass from one measure into the other measure. So kind of the most robust way of doing that has been introduced by Kantorovich, a Soviet mathematician of the last century, who said we should really look at kind of probability measures on the product space, transference plans, pi, which have the property that if you integrate the second variable, you get the first probability. I mean, now I'm speaking of probability measures because I'm thinking of the mass as being 1. Doesn't have to be. So if you integrate out the first variable, you get the mu measure, and if you integrate out the second variable, you get the target measure lambda. So in terms of probability theory of statistics, you may also say that you're looking for a coupling. You have two random variables which are described by the probability measures mu and by the probability measure lambda, and you look for a coupling, a joint distribution of these two random variables, which maximizes their covariance. So, which minimizes this transport distance. Here I'm taking the exponent p equal to 2. In the discrete case, we've looked at a general p. Now for a while I'm going to talk about p equal to 2. So that's kind of a popular variational problem, which kind of, I think, also plays a role in statistics for the reason I've just said. And it's a way of kind of also defining a distance function between measures, non-negative measures, which have the same mass, which I like to call Wasserstein distance, but there are other names, Kantorovich, Rubinstein distance. So that's the infimum, which in fact is a minimum by soft theory. That's a convex variation problem. So the infimum is attained, and that defines the square of a metric. In fact, the triangle inequality is not immediately obvious. You need something like disintegration of measure to prove it, but here I'm asking you to believe it. So that's optimal transportation as a very general in its very general definition and robust definition. This slide is supposed to explain the connection between this variation problem and a famous partial differential equation, which goes by the name of Monge and Ampère. Monge was the first person who wrote down an optimal transportation problem before the French Revolution. So So here again is the variation problem. You want to minimize this cost functional among all transfer plans, so all probability measures or all measures, non-negative measures on the product space, which have marginals mu and marginals. Let's for a moment just look at the Lebesgue measure. And so there's always one candidate for this, a competitor, a candidate for this matching, which is the product measure. But the product measure never is the optimal one unless both measures are, single Diracs. In fact, you can show that the optimal plan in the product space very much concentrates, as indicated on the previous picture here. So it has a support which is not 2D dimensional, but which is only D dimensional. And in fact, the right way. In fact, there is a soft kind of convex analysis which tells you that the support of this measure is contained in the graph of a subgradient of convex function. And so there's always a convex function, sometimes called the Kantorovich potential psi, which describes where this kind of coupling is supported. And using this gradient of a convex function and the fact that a convex function is classically differentiable in Lebesgue almost every point, you can kind of rewrite the condition that the marginals are mu and lambda as this condition which has to hold for all test functions for all observables zeta. And now if you use the transformation rule, you see that this, in fact, so if you replace this integral, if you change variables y to x, also on the right-hand side, you see that this condition is equivalent to the following partial differential equation. So you take this map, you take its differential, which is the Hessian of this map, so the second derivative, and you get a condition on the determinant of this quantity by the transformation rule, and the determinant has to be equal to mu. So that's the Monge-Ampère equation. It looks kind of at first like a somewhat strange equation. You're seeking convex functions. You look at the Hessian, at the matrix of second derivatives of this convex function, and you take the determinant, and you want to describe this determinant by the target, or in this case, it's the original measure. So that's the Monge-Ampère equation. And just as kind of, in a certain sense, as a history of PDE, it played a pivotal role as kind of a very natural partial differential equation, which goes by the name of fully nonlinear. So you could express this, but that's just in a certain sense language or writing. You could express this equation with help of a function A on matrix space, on, if you want, space of symmetric matrices, and you could express this equation by saying f of d second psi is equal to 0 if you define the f as determinant a minus 1. And then this equation is what's called an elliptic equation, because this function f is strictly monotone with respect to the order which you have on symmetric matrices, so the difference being positive definite. Therefore, it satisfies a comparison principle. Therefore, you can make sense of it in the sense of viscosity solutions. But it's extremely nonlinear and degenerate. And the reason is that it has a huge symmetry group. It has a non-compact symmetry group. Namely, it's invariant under SLD, under the space of all affine transformations which preserve the determinant. So it has a much larger symmetry group than our beloved or simplest elliptic equation, which is the Laplace equation, where this function f would be the trace. So the determinant in this sense is very different from the trace, where the group would be, the symmetry group would be compact, all the rotations. And this degeneracy leads to the fact that you may have pretty irregular solutions. There is one famous example by Pogorelov, which kind of wrote down a solution of this equation, a viscosity solution of this equation, in at least three-dimensional case, which is not twice differentiable, and which in fact is not strictly convex at an entire line. Because in a certain sense, I mean, this tells you that all the eigenvalues of the Hessian have to, you know, if you take the product, have to be equal to 1. But that can be achieved by having one of them 0 and the others infinity. And that's, in a certain sense, what's happening here, and therefore it's not C2. And then I think it was one of the big breakthroughs in PDE regularity theory when Caffarelli in the 90s proved that this is really the worst case. So this very explicit example by Pogorelov is the worst case that can happen. So this makes this equation a very interesting equation because it's at the crossroads between the characters of variations. It's the, if you want, the Euler-Lagrange equation of this ubiquitous problem of optimal transportation. But on the other hand, it's also a prime example for a very interesting PDE in the world of viscosity solutions, in the world of maximum principle, and so on. So it's at the crossroads between fully nonlinear and variation. So that was kind of an advertisement for working or thinking about this equation, or why this is an interesting partial differential equation. Now I want to return to this problem of matching. And by the way, when should I stop? Can you tell me about 10 minutes? 20 minutes. Okay. Yeah. So I want to return to this this problem of matching, and I want to tell you about the heuristics of Giorgio Parisi and his group on this problem, which then in the end we, others and we were, contributing to make more rigorous. So here comes the heuristics of Giorgio Parisi. I mean, I'm sure you know that he's a famous Italian physicist. So, and it's best explained in the case of semi-discrete, what's called semi-discrete matching. So when you try to look at the optimal transportation between this random point cloud and the Lebesgue measure. So instead of having two random point clouds, you have one random point cloud and the uniform measure. So that's in a certain sense very natural from the point of view of statistics. You look at how close an empirical measure is to its distribution. But now you do it for a very simple base measure, which is the uniform distribution. So, so he was aware that this is an optimal transportation problem, and that the Monge-Ampère equation is, in a certain sense, a description of the optimal transportation problem. So he wrote down the Monge-Ampère equation, and he subtracted one on the side of the determinant and on the side of the measure. And then he was, or they were looking at this measure, which is on the right-hand side. So that's the this empirical measure mu, which is this bunch of Dirac measures in the Poisson point process, and the uniform background measure. So it's like, think of many positively charged particles in a plasma of electrons. So overall neutral. And so that means that this right-hand side, because it's overall neutral, if you look at it from afar, so if you look at it at scales which are large compared to the particle distance, to the distance between the ions, it looks like neutral. So if you if you look at averages of this kind of this rough right-hand side, it looks neutral. So in other words, the right-hand side is small on large scales, which, if things are okay, should mean that also the left-hand side is small and large scales, which means the Hessian should be close to the identity, because the determinant of the identity cancels with 1. So, but then one knows that if you linearize the determinant around the identity, you get the trace. The trace is the linearization of the determinant. So, so instead of looking at determinant minus 1, you might hope that the trace, which is in fact the Laplacian of this potential, might give you a good approximation. So he said we should expect that the transportation distance, so the gradient of the Monge-Kantorowicz potential, which tells you where my particles are mapped, minus x, where the particle originally was, should be given by the gradient of a solution of a much simpler linear equation, which is the Poisson equation. And then once he was at that step, he was able, or they were able, to draw kind of a lot of interesting consequences from this representation. So in a certain sense, he made the connection between a problem of optimal transportation, a discrete problem of optimal transportation, and kind of a standard electrostatics equation. But of course, it was completely uncontrolled. And what, you know, on the one hand, Ambrosio, Stra, Trevisan, the core workers in Pisa did, and what we're doing is try to give this kind of a rigorous foundation. And so in order to make this a little bit more rigorous, let me explain it what it could mean in a more rigorous way. So again, we start from an optimal transportation problem between a general measure mu, which might be this random Dirac measure, and the Lebesgue measure. And we want to say that on large scales, this rough measure is close to the Lebesgue measure. So the natural way is to do that in the intrinsic topology, to say that within, you know, in the Wasserstein metric, this rough measure is close to a uniform measure, which is essentially stated by this condition. And if that's the case, then we would hope that the displacement, so the blue thing is related to the optimal transportation problem, that the displacement is very well described by the solution of this linear equation, by the gradient, by the field in the language of electrostatics of this Poisson equation with this charge distribution. And on large scales means that we have to take averages with respect to some bump function, some mask function, which we choose once for all. So that's in a certain sense a more mathematical formulation of the heuristics which I presented on the previous slide, and that is exactly what the theorem from the work with Goldman and Huysman states, that on the one hand you have a very general problem in optimal transportation. On the other hand, you have this very simple PDE, and provided that your measure on large scales is close to the Lebesgue measure with a certain rate that depends on the radius you're observing, provided that is true, then indeed the averaged displacement is close to the much simpler object, which comes from the Poisson equation. So that's kind of really, in a certain sense, putting rigor, kind of a quantitative linearization of what was done by the physicists on the heuristic level. So in the last minutes, let me tell you that you know, how we got this result, and that it, in a certain sense, relies on PDE regularity theory. And so now that's the perhaps slightly more technical part. So I don't know how, I mean, some people of you will have kind of perhaps heard of de Giorgi's approach to the regularity theory of minimal surfaces. So, which is kind of, I think, one of his strategy, one of the kind of amazing achievements of last century, and it goes by, so a crucial step in that theory is what's called a harmonic approximation result. So, which roughly speaking says the following. If you have a minimal surface, so an area minimizing surface, and you know that somewhere it's already pretty flat, then, after a change of coordinates, so it sits in a kind of a thin cylinder, you can give a good approximation by the graph of a harmonic function. And since you understand harmonic functions extremely well, you inherit the good properties of harmonic functions to learn that your minimal surface on a smaller set is even flatter. And this way you can prove a regularity of minimal surfaces up to dimension 7 and can characterize the singularities. And now it turns out that very much the same principle holds for optimal transportation. You can show that if you have an initial smallness of the problem, which corresponds to the flatness of minimal surface, if you know that your data, your measures, in this fact we can take two arbitrary measures, if your measures are close to Lebesgue in the weak topology, and if you know that your local energy, the transportation cost of the particles, which, of the mass which is locally transported, if these two things stay below a certain barrier, a certain threshold epsilon, then you can show that your displacement is very close to the gradient, to a harmonic gradient. So that's very much the same philosophy of the regularity theory in minimal surfaces, and it's very different from the famous regularity theory of Caffarelli, which is based on maximum principle. So in a certain sense, it's the same problem, but another approach to regularity theory, not maximum principle based, but based on the variational structure of the problem, which allows to treat completely general measures, which is important for the matching problem, whereas the approach of Caffarelli, in a certain sense, is limited to measures which have Lebesgue densities bounded away from 0 and infinity. So that's in a certain sense the main result under the hood for what we do. And okay, perhaps I can skip this slide. That's just telling that this is kind of a very natural result. You would get something very similar if you look at kind of more standard nonlinear PDE. And yeah, so perhaps how much? When should I stop? A few minutes. Okay, so then I will also not give you this slide. This is, although it's an interesting slide because it tells you how to get this harmonic function, you need boundary conditions. And in fact, you need Neumann boundary conditions. And you have to take the Neumann boundary conditions which come from the underlying optimal transport problem. In a certain sense, you have to kind of keep track of all the particles which cross the boundary of your given ball and take this net flux in and out as your Neumann boundary data for your harmonic function in order to get the good approximation property. And that essentially is something which I already said in words, that this is very close to what famously has been done for minimal surfaces. There's really a dictionary between things which have been done there and which are done here. Okay, so that's the summary. So I started with kind of this, if you want, combinatorial problem and statistical problem with interesting phenomena at critical dimension. And what I like about this problem is, you can make the connection to something unexpected, namely to partial differential equations, to regularity theory. So areas which, at first sight, you wouldn't connect with this. And I've written down a couple of kind of questions you could ask now in the sequel. I think in many ways this problem of optimal matching is an active problem right now, and with several groups working on it. And I think then I will stop. I'm sorry for being almost a bit over time.
Questions from the audience? Okay, let me just ask. So in your final result, your measures were given to be arbitrary. So my question is that straightforward that you can generalize? You started with the Poisson process, so this shot noise. So in fact, you can treat other kind of noises, or?
Sure. So I mean, the main result, the main results which I presented are completely deterministic, and one could apply it to kind of more hyper-uniform types of noises. I think people have been looking at that, but then, in a certain sense, the two-dimensional case is no longer that interesting because you would not see this logarithmic divergence. But in principle, the main part of the work is unrelated to the specific features of the randoms.
Okay, thanks. And another thing, so at some point you mentioned kind of non-existence for p equal to 1 case, and is that connected to something that you said in the end, or?
So it's related to. So for this non-existence result, we need this harmonic approximation result. So this, I've written it down for p equal 2. The general p case we get from a result by Lukas Koch, who proved the same thing for any exponent p, where you have to take a solution of the p Laplace equation. And but the problem is that that requires, in a certain sense, still the strict convexity which is present in the p Laplacian. And when you go to p equal to 1 or p equal to infinity, you lose that. And also the regularity theory is more, for the p Laplace equation, is more solid. So so it's really related to the fact that we cannot kind of get an analog of this here for the p equal to 1 Laplacian. Where in fact, so it's dual. If here you have a power p, then you have to take the p star Laplacian. So it's in fact something which on the L infinity Laplacian.
Okay, thanks a lot. Any other question? So if not, I would press. Oh, yeah, sure.
When you showed that, the first result you showed about the Hungarian school, it seemed not to depend on P. It seems that it does not depend on P, on the exponent.
That's correct. That's correct. So there, I mean, the scaling is goes down all the way to p equal to 1. However, for p equal to infinity, that's the result by Talagrand, you get a different exponent. But in principle, you would believe that the non-existence result also holds for p equal to 1. Just with our technology, at least right now, we're not able to show it. Everything else indicates that it should also be true, that things should not behave completely differently for p equal to 1. However, differently for p equal to infinity.
But the constants appearing in the expansion depend on P.
Yes, correct. Correct. So in fact, you can characterize them for p equal to 2. You can prove that asymptotically they exist for any p in dimension 2, in the critical dimension.
Okay. If there are no other questions, I would thank Professor Otto again. join upstairs now, at ground floor there is refreshment, and tomorrow there is a PV seminar by Professor Otto again for differential equations.